Okay, so today we're going to talk about implicit differentiation. And to kind of explain this, I think it's best just to do a motivating example so that we understand what's going on. So consider the equation x squared plus y squared equals 1. Okay, now this is the equation of the unit circle. Okay, and when we think about differentiation, remember that one of the ideas behind differentiation is to find the slope of the tangent line. I mean, the derivative is the slope of the tangent line. And if you look at this picture here, the notion of a slope of a tangent line still seems to make sense. We can take a point, we have a curve, we can find the slope of that tangent line. Okay? But notice here that this is not something where we have y explicitly defined as a function of x. And when I say explicit, explicit simply means that the y is isolated. Okay, and that of course means two things. It means that y is by itself on one side of the equation, and then on the other side of the equation there is no y's. Okay, it's just going to be in terms of x's. And that's everything that we've dealt with so far, except maybe that last example with logarithmic differentiation. So we're going to want to do the same thing here in a very similar type of way. We want to find dy dx. And again, we have an equation and not just an expression to take the derivative of. So what we can do is we can take the derivative of both sides of this equation. And we can basically solve that way. So notice, of course, that the derivative of the right-hand side, because this is a constant, is just 0. But what about the left-hand side? Okay, this is a little bit different. Well, the first term is going to be pretty normal. That's just going to be 2x. But what about the second term? How do I take the derivative of y squared? Okay, that's a good question. And again, we're taking the derivative with respect to x here, not with respect to y. So it's not just going to be 2y, which is what you might think. But what you want to think about here is that y is sort of a function of x. Okay, so y is sort of something of the form like y of x. And really what we have going on here is we have something that sort of resembles y of x squared. And if I were to take the derivative of this thing, really what this would be is this would be 2y, okay, of x. And then since y of x is itself a function, this would be y prime of x, or perhaps dy dx. So when you take the derivative with respect to y here, we're applying the chain rule. We're assuming that it in and of itself is a function of x. So this is going to be 2y, and then we can either write y prime of x, or we can just write dy dx. And we get something like this. Okay? Now, in order to find dy dx, we're going to solve for the dy dx part of this in the equation. So we're going to need to subtract 2x from both sides. And then we're going to need to divide both sides by 2y. And if we do this, we get that dy dx is equal to negative x over y. And that's going to be the derivative. Notice that this is in terms of x and y, so it doesn't just have x's in it. But we can still use it to find the slope of the tangent line at particular points that are on this unit circle. So here, remember that we found that dy dx is equal to negative x over y. That's what we found in the last example. So what I want to do is I want to find dy dx at this particular point. You should notice here that when we deal with implicit curves, we can't just choose any point that we like. You know, if I have y equals f of x, I can find f prime of whatever, and that works. But I need to make sure that this actually satisfies the given equation here. And if you do a little bit of math here, you will see that 3/5 squared plus 4/5 squared is going to be on the unit circle. And just to kind of approximate where that might be, we're going to say it's probably about right here. Okay, so what we can do is we have this equation. We just plug in the x value, negative x over y. So if I want to find dy dx at the point 3/5, 4/5, this is the notation we would use. This is going to be negative 3/5 divided by 4/5. And remember that anytime you divide by a fraction, you just multiply by the reciprocal to get the answer. So this is going to be negative 3/5 times 5/4, and this is going to be negative 3/4. So again, the interpretation here is that if I find the point 3/5, 4/5 on my unit circle here, then the slope of the tangent line at that point is going to be negative 3/4, which, again, I'm just estimating, but you can kind of see how that could possibly be negative 3/4. It's obviously a negative slope, so if we find the right point, that will be it. Let's do one more example here, just to show you how this works in a more complicated case. If I want to find dy dx here, and again, I could also use y prime, which I think I'll do in this example. So these are interchangeable. So I need to take the derivative of both sides. So the derivative of y cubed is going to be 3y squared, and then because it involves a y, we're going to add that dy dx, that y prime there. xy, we're going to have to use the product rule here. So the derivative of x is just 1, so that's going to be y, plus, and then the derivative of, we're going to write x times the derivative of y, and again the derivative of y by itself will just be y prime, equals, and then since the right hand side is just in terms of x's, that's just going to be a normal derivative, 3x squared minus 1, and that'll be it. Again, we can try to solve for y prime here, and again, the way that we do this is we basically collect all of the terms here with a y prime on one side of the equation, and then everything else on the other side. So I'm going to subtract y from both sides here, okay? And then that's just going to leave me with 3y squared y prime plus x y prime equals 3x squared minus 1 minus y. And then what we want to do is we want to factor out these y primes here. So that's what we're going to do. We're going to factor out a y prime. So this is going to be y prime and then 3y squared plus x. And then the right-hand side will still be 3x squared minus 1 minus y. And now we have something that looks like this. We can isolate this y prime, and this will be 3y squared plus x. We'll just divide that by both sides. And then that cancels, so that means that y prime will just be this right here. Again, you could also write dy dx, and that's perfectly valid as well. So again, our final expression is going to have both x's and y's in it, but this is perfectly valid and it works. So, as always, I hope that you found this video helpful, and take care.